Okay, guys, this last part is on reaction mechanisms. Kind of the process at which the reactants react together to make products. So factors that affect reaction rate. Again, temperature is one of those factors that will affect their rate, will increase the rate of the reaction. Frequency of collisions, orientation of the molecules, and energy needed for the reaction to take place, which is known as the activation energy. So we're going to go through each of these. Frequency of collision. So the more often that the reactants collide with each other, the more opportunities they have for reactions to occur. So if there are more molecules, the reaction rate then goes faster. So if you increase the concentration, that brings in more molecules, and so we can get more collisions, and that will increase the rate. So let's look at orientation of the molecules. Molecules can often collide without forming a product. So if they're not aligned correctly, reaction is not going to occur. So aligning the molecules properly will lead to chemical reactions. Again, remember, bonds have to be broken and made to make products. If you remember, breaking bonds is an endothermic process, and forming bonds is an exothermic process. So this is a little example down here with the diagram. So you can see the little two green are supposed to be the chlorine. They have to be aligned to hit each other in order for them to go off as a molecule, chlorine Cl2 here. Okay, if they're aligned this way, the chlorine's far away from that other chlorine, so when they collide, no reaction would occur. It would stay just the same. Okay, let's look at temperature and the rate. So temperature basically is looking at the kinetic energy of the molecule. So as temperature increases, the rate's going to increase because you're increasing their energy. And if you increase their energy, that's going to cause more collisions, and you get a higher rate of the reaction. So more molecules, again, will have more energy to reach that activation energy that they need to get to. So two things are important here. It is the amount of energy that the atoms have when they do collide, and the orientation. Okay, and so again, the more energy they have, the more collisions they're going to have. Okay, so let's look at energy needed. So this is your activation energy we're talking about here. So this is the minimum energy needed for a reaction to take place. And again, that's called the activation energy. It basically is the barrier that has to be overcome for the reaction to move on. Much like this golfer trying to get over that hill to get into the hole. All right, let's look at an energy diagram, also known as energy profiles. We did this last year. So on the X here is the progression of the reaction, and then this on the Y is the increase in energy. So reactants are going to start with a certain amount of energy. Again, in order for the reaction to occur, we have to break the bonds within the reactant, so energy has to be absorbed in. So you notice my energy goes up. So I hit a transition state. Now, if you remember from last year, this transition state is known as the activated complex. So once that is formed, then it can go further on to make the product. So when the bonds are being formed to make the products, energy is released, and then we make our final product. So you'll notice that their products are sitting at a lower energy than where it started with the reactants. So this is an exothermic profile. Remember this from last year. Okay, something a little new this year is called the distribution of energy within the molecules. So if you have like a sample of gas at a specific temperature, that is measuring the average temperature. But each individual gas particle or gas molecule will have its own energy. And so again, we're just taking the average of that. Now, let's backtrack here. This little diagram here is underneath this curve where it's blue. Underneath here is supposed to be a representation of all the gas particles in that sample. So you can see that some of these particles have very low energy, and then some have very high energy. So again, energy is in terms of kinetic energy, which is temperature. Again, we have a lot of molecules here at a lower temperature. And where the little dotted line is where they need to reach to get to that activated complex, to reach that activation energy, so they can go on and make the product. So you'll notice under the blue curve, there's not many molecules in this little shaded blue area that have enough energy to make the product. Now, if you increase the energy, meaning increasing the temperature, you'll have more molecules colliding. They'll be at a higher temperature, more kinetic energy, so they would actually have enough energy to go over and make the product. So you'll see underneath the curve here, the red curve, all the way down again to past the blue. This area right here is showing more molecules at a greater energy so they can get over that activation energy to make the product. So what does it mean by reaction mechanism? What is meant by rate mechanism, and what is the rate determining step? So we're going to go through that. Reaction mechanism basically is a description of the path of steps by which the reaction occurred. Meaning, like, the reaction can occur in like 1 step, 2 steps, 3 steps, multiple steps. This is how you determine it. So you need to locate the slowest step, which will be indicated in the information that you're given. So for any step, the order with respect to each reactant is the coefficient in a chemical equation for that step. Now, the rate determining step is actually going to come from the one that is the slowest. Let's say you have a relay race. You have 4 runners. You have 3 runners that are really fast and 1 that's really slow. Now, the one that's going to control their overall outcome for the race is going to be the slowest runner, because he's going to determine how fast the overall group is going to finish the race. Okay, so we always write the rate expression according to the slowest step, because that's the one that's going to determine how fast the reaction is going to occur. The rate expression can only contain species found in the overall equation, though. So I'm going to show you what I mean by this. Here's our first example. Now, this reaction happens in 2 steps. We have step 1 and step 2. So we have NO reacting with Cl2 to make NoCl2. Now, NoCl2 is taken further and reacting with more NO to make NoCl. Now, when I write the overall expression, I have to combine these together. You'll notice that NoCl is produced in the first step, but used up in the second step. So basically, it's canceled out. So when I bring everything down for my overall step, I get NO plus Cl2, giving me NoCl. Now we have 2's here just to balance out the equation. Now I need to write a rate expression for this. So I'm going to write out my regular rate expression. Let's move over here. We're going to go, bring it all back up so you can see this. I forgot to cancel this out. This is supposed to be a line through here. Now, when you look at the overall expression, the rate expression can only contain NO and Cl2. It cannot contain this NoCl2, because NoCl2 is used, are produced in the first step and used in the second step. This is known as an intermediate. Intermediates cannot be in your rate expression. It's called an intermediate. Okay, so if I write, again, I have to write my rate according to the slow step. So when I write this, I'm taking the second step, because that's my slowest step. That determines how fast this reaction is going to take place. So I write rate equals, now K2, I just put 2 here because it's for the second step. And then I write those 2 reactants in. And you'll notice that this is a 1 here and a 1 here, so those are going to be my orders for each of these. That's going to be my exponents. But again, I cannot include this NoCl2 because it's an intermediate, because it's not in the overall equation, so I have to get rid of it. Now, if you look at this equation right here, you notice there's a double arrow here. Okay, This means I have an equilibrium expression. Now, equilibrium expressions, I can write another formula for that. We do this in equilibrium, so we have our products over our reactants. And now I want to get rid of NoCl2, so I'm going to rearrange this whole equation so that I'm solving for NoCl2. So I'm going to move NO and Cl2 over to this side. So this is what I get. Now, since I have this expression, I can substitute in Kc, NO, and Cl2 into my rate expression and get rid of NoCl2. So again, I have that rate equals, again, the K2, and then I have Kc from this equilibrium expression, and now I have NO, Cl2, and NO. Now I have two of these, so I can combine these together. I also can combine all these K's into one. I just call it K. Okay, so you don't have to write these two, you can just write K at the end. And then you have Cl2 and NO2 squared. Okay, so again, you can just combine those together into 1K. All right, last thing we're going to talk about are catalysts. Catalyst, again, increases the rate of the reaction by decreasing the activation energy of the reaction. It kind of gives it a different mechanism, basically. So this red line right here is showing the uncatalyzed reaction of hydrogen peroxide. It takes a lot more energy for this reaction to occur to make the products. But if I throw in something with bromine and some sort of acid in there, or I should say bromide and some sort of acid, this will actually speed up the reaction. So you see it creates two different paths here. So this is one path, this is two paths. So this is like two steps that are taking place. So it happens at less energy overall. And so I get more of the reactants to go over to make the products. Okay, there's two types of catalysts. There's homogeneous. Again, the reactants and catalysts are in the same phase. And then many times reactants and catalysts are dissolved in the same solvent as seen below. So this is that hydrogen peroxide. And they're putting in sodium bromide, which has that bromide ion, into a solution of hydrogen peroxide in an acidic solution. So you have hydrogen ions in here as well. So it just takes on that equation or that reaction we just saw in the slide before, making the product. So again, homogeneous catalysts just in the same phase. Heterogeneous catalysts means they're in different phases. Often it's a gas that will be passed over a solid catalyst. This is how your catalytic converter works in your car. It's the absorption of the reactants is often the rate determining step. So this process where, here's an example of hydrogen and you have ethane coming across here. They all latch onto this catalyst. So you have this metal catalyst here. It separates out the hydrogen atoms from each other, and then they can recombine on the ethane to make your ethane absorbed, and then it's released. All right, so that's it, guys. Let's go ahead and start working on the worksheet. If you have any questions, you can ask me next week, and we'll go over, try to clear up anything you might have some confusion on. All right, see you later.